Man. All right, good afternoon. We have a week before the vacation. And what we want to do in the week before the vacation, we want to finish the unit 23 and go into unit, finish unit 24, 23 and 24, and then go into unit 25. That's what we are hoping to do. And as far as lab goes, I was told to do this lab, atomic emission spectra. Today is on the schedule. I looked at the lab and it's not much of a lab at all. I suspected that. Anyway, so instead of that lab, we will be doing something similar, but it doesn't take that the information in the lab does not take much time. So we'll have extra time today. So we can go over the homework and I can give you the quiz tomorrow. So that's the idea. And the next, after coming back, you're going to have the exam. And I was disappointed when we talked about the exam, the last exam. Looked like not many people stayed. And I wanted to tell you, I started telling you about certain things and then there was not much enthusiasm, or so I felt about it, and never did finish that. So how to study for the exam, especially when you have open book exam, open notes exam, it should make easier to take the exam, of course. If you would be taking this exam at Chabad College, I would not give you open book exam. I would not give you open notes exam. So there's a big difference here, right here. And some of you were saying, we have difficulty here. And true, we have difficulty because of COVID and because of being on the line. It's also, there are some advantages. You have an exam that you can take, that open book exam. What does it mean to open book exam? How do you prepare for the open book exam? Have you had open book exam that you have taken before so that you know how to prepare? Or have you thought about it? Or not? Those are some of the questions I have. And so let's look into those questions and hopefully make it easier for you to take open book exam and get better grade. I mean, learning chemistry is also important, and getting better grade is also important. So that's one of the things I want to do today. And maybe even on Wednesday, because Wednesday we don't have a lab. We have unit 28. So unit 27, maybe we'll finish it. Now, let's finish unit 27. But before that, let me tell you, this morning I was looking at the news and I saw this news that is very pertinent for us today, for going into quantum chemistry, unit 25. So I try to send it to me, the news, in my email, but somehow I'm not getting it in my email. That's what I'm checking right now, my email, and I did not get it. I don't understand that. I do the right thing, mail it to me. Okay. And it says gone. And over here, I don't see it coming. I don't know what's going on. But anyway, the news is about, listen carefully, kind of strange thing. Does time really run faster at your head than your feet? You heard it right. Does time really run faster at your head than your feet? That has to do with quantum mechanics. And we talk about quantum chemistry, and then it goes into explaining what does that mean. And some of it is relevant to us, some of it is interesting, some of it is goes over our head, my head too. Anyway, so hopefully I'll have to read that some of that to you today. Anyway, so if it is in the news, that means quantum chemistry and quantum mechanics is becoming part of everyday life. So we'll go into that unit, but let's first take care of the last unit, 23 and 24. 3 laws of, okay, let's get rid of this now. I'm not getting my mail, change. And we go into the last part of this number 2. And I got the number 3 printed. The guidebook number 3 is already printed. It's sitting at Chabot College. About 9 or 10 of you showed interest in it. The rest of you said you will print it yourself or deal with it yourself. So some of these 9 or 10.
Hey, Professor?
Yes.
What about the other additional book besides the lab manual?
That's what we are talking about, the guidebook, number 3.
What about the other one that's like the graphing thing?
That some of you said that you will be picking it up, and you should. Last week, the person who deals with it was on vacation, so we could not do it last week. And this week, she is going to send out messages to those 8 or 9 people who were interested in doing that, and tell you when you can pick it up at Chabot College. So that's what's happening with that. And with that, if you want to pick up, if you are one of those people who told me that you would need a paper copy of guidebook 3, then you can also pick that up. That's the idea. And the rest I will bring at my home. And then those people who are not going to Chabot College, 2 or 3 people, or maybe 5 at the most, who can pick it up from my home later. And so that will happen this week, hopefully Tuesday. By end of this week, you will have everything, number 3 in paper form, those of you who want it. So that's what that is about. Okay. Now, we are going to go to entropy change in the surrounding are primarily due to heat transfer. That's where we are going. We already talked about this. I'll briefly touch it again. It explains here why.
Professor,
Yeah,
are we supposed to be watching your screen or your face? Because you're not sharing your screen. I'm trying to see what page you're on.
Okay, all right, thank you. My face is not that pretty this morning, I know.
No, your face is perfectly fine. I don't mind seeing your face, but I want to see what you're talking about.
No, no, it's old face. I understand that. It's all right.
No, you're good.
Oh, thank you. Okay, thanks for reminding me, sharing screen and turning on the recording.
This meeting is being recorded.
Okay, I do need this kind of reminding at times, so I appreciate you letting me know.
Yeah, I wasn't sure, and that's why I let you talk a little bit. So I'm like, all right, I think he's supposed to be sharing his screen. Thank
Sure,
you.
you ask me, and you know that anytime you need to talk, you just jump in and say something. You guys know that, so that's good. All right, so you are screen sharing now. Get rid of that, and annotate, and mouse, and all those good things are here. Move these out. Okay, and 200% is okay for everybody, or is that not enough? Everybody? Okay, 200%. All right. So entropy change in the surrounding are primarily due to heat transfer. Entropy change in the surrounding. Surrounding is rest of the universe. The entropy change, entropy meaning the change in disorder, is primarily due to heat transfer. So that's the one we think about. How much heat got transferred into the surrounding? If a lot of heat got transferred to the surrounding, the entropy of the surrounding increases a lot. That's what we would think. That's how we like to think. Well, that is true, but that's not how some people thought about it. And they explain why. And they said that just like last time we talked about city of Stockton 2 years ago. They did an experiment. They said, we are going to give certain amount of money every month to a certain number of our residents and residents on the poor side. And no strings attached. This money, just they get that every month. We don't tell them what to do with it. They do whatever they want to do with it. And some people said, oh, there's socialism. Oh, there's socialism. You should not be doing that. And some people said, oh, well, we know what they're going to do. They're going to drink and they're going to smoke and they're going to squander the money. Of course, that's how it's going to happen. What's the big deal about that? Everybody knows about that. Well, so the poor, 50 or 100 or something, 100 people or 100 families or something like that got this money every month for 2 years. At the end of the 2 years, they found out that these families were much better than before. That they had paid off their debt and they were in much better situation. Some of them were able to find full-time job because they didn't have to worry about every month, hey, where is the money coming from? They had some money coming and they had not to worry about it. The life, the brain works much better when you don't have to worry too much about everyday things like where the food is going to come from. So they actually found full-time jobs after a while, and they are doing much better. So now, hearing that, the city of Oakland said, oh, we are into it too. We're going to do that next year. And there is another city that's also going to do it next year. So $1,000 a month for a poor family is a lot of money. $1,000 a month for a billionaire is nothing. That Jeff Bezos is going to be a trillionaire in a few years. That's what everybody's saying. And he doesn't want to pay $15.30. That's what he pays to his workers. And he doesn't have all kind of other things and works with them very hard. That's what we hear anyway. I don't know. And if that $15.30 become $16.30 or $17.30, what difference does that make to Jeff Bezos? Nothing. He's the richest person in the world. What difference does it make to a person who is working there? There is a difference, and you understand that. So why not? So the thing is that when there is, if the surrounding has a lot of entropy and you put entropy in, more entropy in the surrounding, that doesn't make much of a difference. A billionaire has a lot of money and you give $1,000 a month to the billionaire doesn't even notice that. But you give $1,000 to a person who has not much. If you, that surrounding, his entropy is low, and then you put in entropy, that makes the entropy of the surrounding, effect of the entropy going in the surrounding much bigger than when the surrounding would have a lot of entropy in it. And therefore, it is said that entropy is inversely proportional to the temp delta T, inversely proportional to T. And that's what we see over here. So delta S surrounding, the entropy of the surrounding is inversely proportional to 1 over T. And negative delta S system is inversely proportional to delta S surrounding, because delta surrounding is negative delta S system. So therefore, at constant pressure, delta S surrounding equals negative delta S system divided by T, meaning delta S surrounding can be measured. Now this is something very important, because we wouldn't think, how would you measure delta S surrounding? All you have to do is to know the negative delta S system and divide it by T, and that's the delta S surrounding. And that's the second law, that there comes the second law of thermodynamics. Delta S universe equals delta S system plus delta S surrounding. Delta S universe, we know delta S system where can be measured. Now we know delta S surrounding can be measured. So now we have this equation where both of these things can be measured, so delta S universe can be measured. Or we can rearrange this equation and multiply everything by T and substitute delta H, negative delta S system, or divided by T for delta S surrounding, because we know delta S surrounding equals negative delta S system divided by T. So now in the second law, we substitute all this, and so we come up with this new equation, and you don't have to memorize that equation. I'm not going to ask you to derive this equation either. So delta S universe equals negative delta S system divided by T plus delta S system. Example 6, calculate delta S universe of the formation of methane from its constituent elements at 25 degrees Celsius. And we want to have it at 25 degrees Celsius because that's what we have for our heat of reaction and heat of formation. That's the standard state. That's why we have it 25 degrees Celsius. The molar entropy of graphite is this. Of hydrogen gas is this, H2 gas. I should put in here hydrogen gas. Whenever we talk about entropy and enthalpy, we need to put in our states. So do remember that. And of methane is given to us. So heat of formation of methane is given to us. Also determine if the reaction is a spontaneous reaction. Now this is a big thing, but all we have to know is that these equations are available to you. What you have to do is to figure out which equation to use. And this is the final equation here. So most likely you'll have to use that final equation. So calculate delta S universe. And what is given to us is molar entropy. Molar entropy means entropy of 1 mole of graphite. That's what it means, molar entropy. of 1 mole of graphite at 25 degrees Celsius is this, and hydrogen gas is that, and methane is that. Now heat of formation of methane is given, so we can plug in the values over here and also determine if the reaction is a spontaneous reaction. So this, once you understand which equation to use, there is not much to do with this thing. We just have to plug in the values, and that's all there is to it. So what does it mean? Also determine if the reaction is a spontaneous reaction. For a spontaneous reaction, delta H. For a spontaneous reaction, delta G. Delta G, Gibbs free energy, is negative. We talked about that. For a reaction at equilibrium, delta G, delta G is 0. For a non-spontaneous reaction, delta G is positive. So this is what we remember. Of course, it will be available to you, but you don't want to, this is a simple thing to remember. So I expect everybody to remember that. And that would be, life is easier if you remember that. Okay, there we go. So also determine if the reaction is a spontaneous reaction. So how do we determine that? We determine that by calculating delta G, or by calculating a delta S universe. Delta S universe, when it's positive, that's when the reaction is spontaneous. When it's negative, the reaction is non-spontaneous. So it goes opposite to delta G. Delta S universe. Positive equals spontaneity, spontaneous. And you understand, if it would be negative, it would be non-spontaneous. It would be 0, then it would be reaction at equilibrium. So delta S universe goes opposite to, and most of the time we are not going to talk about delta S universe. Most of the time we're going to talk about delta G. Okay. So we say, we just plug in the numbers over here. Negative delta S system, calculate the formation of methane, universe formation of methane. The heat of formation of methane is given to us, so that's going to be the heat of the system. Now, I want to go back talking about heat of formation. I looked at some of your answers in the homework, and I realized that we need to put more emphasis on heat of formation. So that's where I want to go first before I even go into this question. Well, let me finish this question very quickly. We just have to, delta S system meaning heat of formation, so negative 74. T is going to be 25 degrees Celsius, given to us here. And delta S system is, we can calculate that because the entropy of different parts of the system is given to us. So we just plug in the value in this over here, and we get the answer, delta S universe. And if it is positive, it is spontaneous. So we can tell it that way. Now, I want to go back to this heat of reaction and heat of formation business. And to do that, I'm going to go back into the homework. So let's go back into the homework.
Hey, Professor, after we go back, Any chance that we could go back to this example 6 and just fill it out?
Well, we will go back to it. Yes, oh yes, we'll do that. But before that, I want to do delta H,
Sounds good.
yeah, we'll do that. Okay. I don't want that. We don't want that at all. Okay. Okay.
Hey, guys, just a heads up. If anyone was having trouble with Unit 22 homework for questions 4 and 5 of 24, I just posted a link. It's like a Khan Academy video, and it really helped me understand it a little bit better.
Thank you.
No problem.
Okay, which of the following statements about the heat, and this is a little hard for some people to read, but you might remember. The standard enthalpy of formation is not
This
correct.
problem is from chapter
The
5
heat of
of the
formation
COTS.
of all elements is 0. The correct answer would be the heat of formation of all elements in their natural state at 25 degrees Celsius is 0. This is important. Natural state at 25 degrees Celsius. Okay. All right, starting from here. N2 gas plus 3H2 gas is 2NH3 gas. And that plus 92 kilojoules. This means this is an exothermic reaction. 92 kilojoules is exothermic reaction because the heat is part of the product.
Hey,
So,
Professor,
yes.
I haven't turned mine in yet because remember we were talking
That's
about this?
fine. That's fine, not a problem.
Okay.
I'm gonna go through this anyway.
Do you want me to get off the call for a minute?
Get off the what?
You want me to leave for a minute?
No.
Okay.
I'll give everybody 2.2 extra. So you don't have to worry about that, okay? So if you get correct answer, that's all right, because I'm gonna make sure that everybody gets correct answer for, if your answer is wrong for this one, I'm gonna call it correct and I'm gonna add 0.2 to or 0.3 to everybody, okay? So thank you, appreciate you being honest about this. Okay, so the standard of the reaction of this exothermic reaction is going to be negative 92 kilojoules. Because this is an exothermic reaction, it is coming out of the system, and reaction of this exothermic reaction, the way it is written in this equation. That's what it means. This exothermic reaction, this is the way it is written. Heat of reaction is negative 92 kilojoules. Okay. Next question. 2H2O liquid. Very important to write that because 2H2O gas would have a different situation happening here. 2H2O liquid plus 572 kilojoules equals O2 plus H2, 2H2. This is an endothermic reaction. The heat is part of the reaction, part of the reactant. Heat is a reactant. That means it is an endothermic reaction. Heat is going into the system, and therefore the heat is going to be positive. So heat of reaction for this endothermic reaction is going to be plus 572 kilojoules, or you can just simply say 522 kilojoules. That's okay. Doesn't have to be plus. We understand it's plus. Next question.
Professor, for that one, I didn't put the plus and it marked it as wrong.
I corrected that. I looked at that and I said, that's fine.
Okay.
Okay. The standard heat of reaction of endothermic reaction. Now there is a problem here. I am calling this endothermic reaction, and then I am writing heat as a reactant. So there is a problem with this thing. And if I call it endothermic reaction, this is an endothermic reaction because it's not going to go the other way. This H2O is not going to break it down into oxygen and hydrogen. You have to add energy into it. So I'll have to deal with this question. There is a little bit of a problem with this question. Okay, having said that, next.
So how would that break down? Would that, if it's
Okay,
an exothermic, right?
Let's look at it. All right, let's look at it. So here we have, first of all, this reaction is not a spontaneous reaction. We know that water does not spontaneously break down into oxygen and hydrogen. Everybody knows that. So the way this reaction, so I would say the standard heat of reaction of this reaction in endothermic, I should take it out. So I would say like this, of the reaction of this reaction, the way it is written. Is like that. Okay. Heat of the reaction, this exothermic reaction. Now you see that this is written backwards. This equation is written backwards now. Just the same equation, everything is the same, but it is a reaction that is
Reversed.
reversed. Thank you. And therefore, we're going to reverse the sign. So it's going to be negative 572. I think most people were able to do that. Negative 572 because we reversed it. That's all there is to it. Okay. Now the next one, heat of reaction of this equation. This equation is half of this equation. Everybody see that. So we're gonna divide 572 by 2, and then because we are talking about an exothermic reaction going this way, this is gonna be negative 286 kilojoules. So we are not only flip the equation from here, but we also divided the equation by 2, and therefore we're gonna divide the heat of reaction by 2. Now everybody should realize this equation is the equation making 1 mole of H2O from its constituent elements at 25 degrees Celsius. Therefore, the heat of reaction for this reaction is also called heat of formation of H2O. Heat of formation is the heat exchanged when 1 mole of a compound is formed from its constituent elements at 25 degrees Celsius in their natural state. Constituent elements in their natural state at 25 degrees Celsius. And the product is the compound, and elements cannot be products. You cannot form element. So this has to be a compound. So if we are talking about heat of formation of water, then we are talking about forming 1 mole of water, but then you have to say, is it going to be water liquid or is it going to be water gas? And that will be different. So the heat of reaction of the equation, the way equation is written, is negative 286 kilojoules. Fine. This reaction represent forming 1 mole water from its constituent elements. This heat of reaction is also called heat of formation of H2O, liquid H2O. So heat of formation, not or standard heat of formation, either way is okay. So this is how when we write it, then it's called the heat of formation of water, liquid water. That's what it's called. The heat of reaction of equation is 242. Now look at this equation. This is H2O gas. This is H2O liquid here. And that's the difference here. The heat of formation of this H2O gas is different than H2O liquid. That's what I'm trying to point out to you. And it's called heat of formation of H2O gas. Gas is H2O, or standard heat of formation. It is also called heat of reaction of this reaction. Both of them the same thing. Now, choose the equation whose delta heat of formation is the heat of formation of ammonia. Choose the equation whose heat of formation is the heat of formation of ammonia. What are we forming? We are forming ammonia. Ammonia is the product. Only ammonia is the product. Nothing else is the product. Only ammonia. So we write down NH3 as the product. Now, heat of formation is forming the compound from its constituent elements. Ammonia is made up of nitrogen and hydrogen. So we're going to write down N2 plus H2. That producing ammonia. And now we're going to balance the equation. So we say 1/2 N2 plus 3/2 H2 equals 1 NH3, because heat of formation is always about forming 1 mole of the compound. Compound, not element, of course. So you are forming 1 mole of compound. So when I ask you, write the equation for the heat of formation, write the equation whose heat of formation is the, how would you say it, is the heat of formation of aluminum chloride. So you say aluminum chloride is the product, and aluminum chloride is made up of aluminum and chlorine. So we write down the equation this way. Aluminum chloride is the product. So aluminum plus chlorine. Chlorine is Cl2, of course. We cannot write Cl for chlorine. So we say aluminum plus Cl2. And Cl2 is a gas. So we have to write down gas. And we have to write down aluminum as a solid. And everybody knows aluminum is a solid at room temperature. We are talking about room temperature, of course. And that is forming AlCl3. Oh, what happened? Everything got, okay. Al solid plus Cl2 gas forming AlCl3. That's the correct formula for aluminum chloride. Now we have to balance the equation, making sure that we have only 1 mole of AlCl3 here. So we need here 3/2 Cl2. And we need 1 aluminum over here. Now this is balanced. And this is going to be solid at room temperature. Everybody knows that because this is an ionic compound, and all ionic compounds are solid at room temperature. So this is solid. So this is how we would write the equation whose heat of reaction is the heat of formation of aluminum chloride. It's a mouthful to say whose heat of formation is the heat of reaction of aluminum fluoride. So all compounds have heat of formations. All elements in their natural state at 25 degrees Celsius, the heat of formation is 0. Any questions so far?
Nope.
All right, let's go to the next. Here we go. Look up the table for standard enthalpy, and that should be pretty easy. You don't have to look up for aluminum, 0, bromine molecule, liquid, 0, carbon graphite, 0. That's easy to do. Carbon diamond, of course, is not 0. And 2H2O are two different ones. Heat of formation of element in the temperature state at 25 degrees Celsius is 0. The heat of formation of NaCl is negative 411 kilojoule. The heat of reaction of this reaction given below is 2 multiplied by this reaction. So we write down the equation for the heat of formation of NaCl. We're going to write that down here. And we are forming 1 mole of NaCl. So this is what I write down first, NaCl. And I don't change that. And I'm going to write down something in front of that. Na is made up of Na, and it's made up of Cl, and Cl comes at Cl2. So I'm going to say Cl2 here. And now I'm going to balance the equation, keeping 1 over here. So I need 1/2 Cl2 here. And this is a solid. This is a gas. And this is a solid. So this is the equation whose heat of formation is the heat of reaction of sodium chloride. 1 mole of sodium chloride. And this equation is double that. Therefore, we have double this. Negative 411 multiplied by 2 is negative 822 kilojoules. Negative because this reaction is exothermic reaction, extremely exothermic reaction. Okay. Which of the following statement about heat of formation is not correct? This is not correct. We need to say more than that. The heat of formation of all elements in their natural state at 25 degrees Celsius is 0. That's what we need to add. Okay. Some folks forgot to write the definition because it was not easy to see that this was a question. So we'll take care of that later. Okay, now I hope you have a better understanding of heat of formation. And when you understand heat of formation, that makes it life much easier. Let's get out of here for now. Go back to our question now, heat of formation. Calculate this of universe. So we are going to take this equation from here and we're just gonna put it in there. Dang. Okay. Calculate delta S universe. So we take this equation from here. Copy. And text. Write the chemical equation. Chemical equation, I have to say that chemical equation, otherwise people write, they don't know what equation to write. What chemical equation are we going to write? We are going to write the heat of formation of chemical equation that is about the heat of formation of methane. So what is the product? Methane, heat of formation of methane, forming methane. So we're gonna write down methane is a product. CH4, gas. Everybody knows methane is a gas at room temperature because everybody knows about cooking gas. Now, it has to be made up of carbon, And this carbon cannot be diamond, it has to be graphite, so we have to say that. Carbon graphite. Plus 2H2. That will give us 1 mole of CH4. So this is the chemical equation we need to write. And I have to write down 2H2 gas. Write the chemical equation. This is our chemical equation we wrote. Calculate this. We're just gonna now, all we have to do, oops, there's a problem here. Dang. So I'm just gonna plug in the values over here. Delta S universe equals negative delta S system, and the system is this. This is our system, and the negative delta S system is our, this is gonna be this here. And we're just gonna write down kilojoules now because we have 1 mole. Divide that by temperature is 298. Everybody knows 298 Kelvin. K, big K. Plus delta S system. And that delta S system we will have to calculate. This is a mistake, but delta S system we will have to calculate. So we're gonna calculate it over here. Delta S system equals sum of delta S product minus sum of delta S reactant. Simple equation. Now remember, delta S is not, there is no formation here. We are not forming anything here. Delta S is entropy, change in entropy, and we are not forming anything here. Changing entropy. So now we have, what do we have next? Product is CH4, and the heat of entropy of methane is given to us 186.1 joules per Kelvin. So that's 186.1 joules per Kelvin. And that is, we're gonna put it into parenthesis here. Oh, this is minus, sorry about that. This is here is minus. Yeah. This sign, it's not an equal sign, it's a minus sign. Sorry about that. Yeah. Minus, there we go. Minus sum of delta S reactants. We have the reactants, 2 hydrogen gas, 2 mole of hydrogen, 1 mole of graphite. Graphite is 5.686 joules per Kelvin. So we write down 5.686 joules per Kelvin plus 2H2O, not 1H2O. So 130 multiplied by 2, 261.2. 261.2 joules per K. And I would suggest that you use this parenthesis and the brackets Not just parentheses, also use brackets like this so that your signed stay proper. So now we just do the calculation, and that's just adding and subtracting. 261.2 plus 5.686. That's a negative number. So, and 186 is a positive number. 186.1. That equals negative 80. That equals negative 80.8. I want just one number after the decimal point because I have one number after this decimal point here. I have 3 numbers after the decimal point and 1 after the decimal point here. I want that much. So joules per Kelvin. And this is our delta S system. So we're going to write it down here. Plus negative. I'm going to put it in the parentheses because I want to make sure my sign doesn't get lost. 80.8 joules per Kelvin.
Do we have to convert it to kilojoules?
It doesn't matter. Right now, we'll have to convert it to kilojoules because we have kilojoules over here and we have joules over here.
Yeah.
So we have to convert that. So now, going further,
Hey, Professor, could you slide the screen up just a little bit?
that's what I'm doing right now.
Okay.
And now
So would,
I write this down. If you have not written this down because it got changed, right? It's got moved. So okay, 80.8, 80.79. So we got that fine. Negative 80.8. I want 3 sig fig over here. Okay. And then we have let's get rid of this clear. And now we take this and we plug it in over here. Delta is surrounding.
so delta S system would be the 186.1 joules over Kelvin
Right.
minus the 5.684 joules over Kelvin plus 2.612, right?
Well, we calculated a delta S system and then we want to put that into this equation now. Or
Okay.
we go directly into this equation. So put it into delta S system into this equation directly. I have done here, I have taken steps by step, but you don't need to do that. I wanted to show that you can do it step by step, but you can also use this equation directly. So then you just plug in this number over here. This is the delta S system, and this is our delta S system. So we plug it in this number. That's what we did over here. And
Yeah.
then delta S, delta H system. That's going to be that. And the T is 25 degrees Celsius or 298. And then we want to make sure that this joule is converted into kilojoules, because this is going to be in kilojoules. So when we do that, delta S surrounding, where we equals this, but you don't have to remember this equation. In fact, I don't think I'll ask you about delta S surrounding. So just this equation is the important equation. And that's all for now. Then we're gonna say delta S system, just delta S surrounding. Surrounding is this one, and system is this one. So we're gonna add these two up, and and that's going to give us delta S universe, and that is gonna be negative. Everybody can see that just adding these two numbers up. And therefore it's a non-spontaneous reaction. Because delta N universe, when it's positive, that's when it is spontaneous reaction. If it is negative, it's a non-spontaneous reaction, delta S universe. Okay, next, entropy and equilibrium state. We talked about that already. At equilibrium, delta S universe is 0. System equals the surrounding. That's what that means. Example 7. Calculate delta S universe of the process. This is a reversible reaction. So we already know the answer. It has to be 0. At 352 Kelvin, the boiling point of alcohol. This is alcohol. When alcohol or anything boils, at that temperature, there is a reversible reaction going on in a closed container. So if we take water, we are boiling it in a closed container, there is a reversible reaction going on. That is, water liquid is going to convert into water vapor, and water vapor is going to convert into water liquid, and both of the conversions are happening at the same rate. Therefore, no net change in the concentration of liquid or the gas. That's what equilibrium is. So we want to find out if that is the case or not. That's what it is. The answer is already known to us. Okay. Delta S at equilibrium, delta S surrounding equals this, and delta S so we have this here once again. Universe equals this and this equals that. So delta S surrounding equals delta S system divided by temperature. Heat of vaporization of this process is 38.6 kilojoules. It is you'll have to put energy into the system in order for it to boil. Therefore, this is positive. So we're gonna say delta S system is 38.6, and we're gonna divide that by 25 degrees Celsius. 38.6 kilojoules divided by 298 Kelvin. Delta S universe equals this surrounding plus delta S system. So now we know the surrounding, so we put it in there.
Shouldn't the temperature be 352 or no?
We're gonna, that's a good question here. We have a problem here. This means 25 degrees Celsius.
Yeah.
And this means 66 degrees Celsius or somewhere there. 78, 78 probably. So that is a problem here. How are we going to solve that problem? We're going to solve that problem by saying that the heat of reaction is dependent upon temperature, but excuse me, the temperature dependent is very low, and therefore we can assume that there is no temperature dependence at this low temperature of 352 Kelvin.
Okay. That makes sense.
That's how we are going to deal with that. And then, as you said, we need to put that 352 over there. Thank you. Yes. Uh, 38.6 divided by 352. And the unit, Kelvin, and this is kilojoules per mole. This expression represents, I want you to remember that it represents delta S surrounding. That's what it represents, this here together. And then delta S surrounding plus delta S system equals delta S universe. That's where we are going. Delta S universe. There, that's better. So delta S system is 109.7 joules divided by Kelvin. And this is joules, and this is kilojoules. So we'll have to deal with that.
So we do a conversion, like in the problem, the 109.7 kilojoules, would you then times it by joules and kilojoules in the problem to make it equal? Like
You can
put
just write
parentheses around it?
0.1097 joules, kilojoules. Just, you don't have to show me anything else then.
We can just do it.
Right, yeah. Now I'm gonna come back to this after, excuse me, after our break. So let me go further here. Criteria for spontaneity for exothermic reactions. The exothermic reaction increases the entropy of the surrounding. And these are a lot of words. There are a lot of words, and they have to be said very, very carefully. So we are saying, what happens? Exothermic reaction, are they always spontaneous or not? And we know that that is not the case. Exothermic reactions are not always spontaneous. So when is exothermic reaction spontaneous? What are the criteria for it being to be spontaneous? That's what we are saying. What does it mean by spontaneous? That means the reaction is going to happen on its own, without you putting energy into it, without you doing anything into it. That's what a spontaneous reaction means. So rusting is a spontaneous reaction. You just leave the iron alone, and after a while it will rust. It's a spontaneous reaction. sodium hydroxide plus HCl is a spontaneous reaction. All you have to do is to mix the two and they'll react. But a match burning, starting to burn is not a spontaneous reaction. The match stays there for years without burning, unless you put energy into the system by striking it. So that's not a spontaneous reaction. But once the match is burning, that burning of the wood itself is spontaneous. Once it's burning. Okay. So that's what we mean by spontaneous reaction. Exothermic reaction, the delta H of the system increases the negative delta H of the system. This is an exothermic reaction. The delta H of the system is negative. Increases the entropy of the surrounding because it puts heat into the surrounding, so entropy is increased. If the reaction is also increases the entropy of the system, then delta S universe is positive and the reaction is spontaneous. Now, these kind of questions are not going to be there. As long as your understanding is okay, I am not going to ask you even in the multiple choice question this thing. It's a full of words and every word has to be just right. Otherwise, one little mistake and it's all can be wrong. And that I cannot have in an exam. That's a difficult thing to do. If the exothermic reaction decreases the entropy of the system, then the spontaneous reaction depends upon the size. Now, this is a little hard to understand. If the exothermic reaction decreases the entropy of the system, then the spontaneous of the reaction depends upon the size. How big the size of the two things. This and this. So this depends upon how big the heat of the reaction is. And this depends upon how big the entropy of the reaction is. And they're going to fight it out. That's what they are saying. That because of these adding these two, if one of this is going to be negative for the exothermic reaction, and this is positive, and then if it is a big positive here and a small negative here, then that would give us positive. And otherwise it would be other way. So that's what it's about. Now there is another way of talking about this. It's easier to understand. So we are going to go into that. Same thing here. We talk about spontaneity for endothermic reaction. And instead of talking it about with respect to delta H universe and delta H universe, we talk about it in point of view of delta G universe, and that's easier because delta G, as we have defined, is delta G is the Gibbs free energy. Gibbs free energy. What is it? Why is it called Gibbs free energy? Because Gibbs is the person who came up with the idea. Free energy, what does that mean? Energy that is available to do work. That's what it means. All the energy that the gasoline has, potential energy of the bonds in gasoline, all that potential energy it has is converted into heat energy when the gasoline burns. Now, not all this heat energy is available to do work. Some of this heat energy is going to go into the atmosphere without doing any work. We know that. The car engines get very, very hot. And that heat is just dissipated into the atmosphere without doing any work. But some of this heat energy, some of this, not heat energy, some of this change in energy because of the reaction can be converted into work. And that how much of this energy is converted into work is what is given by delta G. So the free energy meaning energy that is available to do work. So that is Let me put a little zero in here so it's easier to understand. So this is the equation for delta G, and this equation came from this equation that we talked about, and I'm not gonna ask you about these equations over here. So Rxn. So we're looking at this is much better than
Wait,
looking at anything.
what is it? It's delta H RXN minus delta S RXN.
T delta S Rxn, T.
So temperature delta S RXN.
Yeah, and we are gonna go there right now. So
Are we gonna go there after the break?
no, right now.
Okay.
Oops, right there. Delta G reaction is delta S system minus T delta S system, right there, okay? So we took these equations and created a new state function, and that's called delta G system. So now we got out of all this, what's happening with the delta S system, and delta S surrounding equals delta S universe. That's an easy equation, but delta S surrounding equals negative delta S system divided by T. That's not an easy equation to understand. So we got rid of all that, and now we have one new state function, and that new state function is delta G. So this is what we're gonna remember. This is the equation. Of course, it's available to you anytime, but this is the equation that we're gonna put emphasis upon. It's easier equation to deal with. We know temperature. We know we know temperature. We know how to calculate delta S of the system. We know how to calculate delta H of the system, and so we can deal with this much easier. Now we already talked about this here. If delta G is less than 0, then it's a spontaneous reaction. If delta G is greater than 0, it's a non-spontaneous process. And if delta G is at equilibrium, 0, and the process is at equilibrium. The phrase free energy means energy available to do work. For a non-spontaneous reaction, like breaking down of water into hydrogen and oxygen. These days, many people are talking about it. In Science News, you're talking about, oh, let's find an easier way to convert water into hydrogen and oxygen. And some people have claimed that they can do that by using solar energy. So by using just the sunlight. So there is a next big thing. Everybody's saying, well, that would be wonderful, because then we would have free hydrogen available. Solar energy is free. And if you can convert water using solar energy into hydrogen and oxygen, hydrogen is free and oxygen is free. Burning hydrogen gets back up to water, and we get the energy back. So then we can store that hydrogen, and the nighttime, that hydrogen we can burn and make electricity. So everybody's saying, well, problem with solar energy is that is only available during daytime. And that is true. So what are we going to do at nighttime? Well, some people say, well, let's have the wind energy. But wind blows at times and doesn't blow at times. So what are we going to do? Then some people said, well, let's have some batteries, very, very big, great big batteries, like extreme, like battery, like as big a battery as a big store, like Target or something. And that's what's happening in Texas these days. So we would store that electricity, and at nighttime, that electricity will be given out. The other way to do it, they say, is that if we can store the hydrogen gas, then at nighttime we can burn the hydrogen gas and make electricity, and then we can get the electricity out. So interesting things that are happening these days with respect to production of energy. So this is the equation we're gonna pay attention to. And that's what delta G means. That is a free energy available to do work. And then we'll get back into this after the break. So let's take that break. We are taking a 30-minute break these days. Remember that at 1:50 we will be back. Anybody has any questions? You can go for it right now. All right. I wish you happy 30 minutes. It's not such a, it's a cool day today. Yesterday was very nice. Today is a little bit of a cool day, but the sun is shining. We can use some rain, of course, but hey, that's how it is. Sun is shining, so sun is shining. All right. Okay, see you soon.
Thanks, Professor.
Bye.